Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in pretty much any college mathematics course, please consider subscribing, checking out our playlist, watching videos, liking, commenting, sharing those videos. Those are really simple interactions that you can do that help us out with the YouTube algorithm and allows us to reach a bigger audience. Let's go ahead and get into the current video. I want to take a look at the specific topic within differentiation called the chain rule. Now, when you're in your Calc 1 course and you're learning the differentiation techniques, the product rule, quotient rule, etc., you do a differentiation rule that applies to every single algebraic combination. If I add two functions, how do I differentiate? If I take a product of two functions, how do I differentiate? Well, the chain rule is the differentiation rule that applies to composition of functions. And as a quick reminder, let me give you a pair of functions. Let's say f of x is sine of x, and g of x is equal to x cubed. What I mean by the composition is f composed with g, right? This little circle in between the two functions that represents the composition operation. And what it represents is I use the function that's on the right as an input for the function on the left, meaning this would be f evaluated at g of x, and g of x was x to the third. That gives me f of x to the third. And the idea is the input now goes into f. X to the third as my input gets plugged into the function f, meaning it gets plugged into the sine function. And this would give me sine of x to the third. Now notice that this function right here is not applicable to your previous differentiation rules. It's not a product, sum, quotient, constant multiple of those functions. It is a composition of those. Similarly, if I did the reverse composition, if I did g of f, that means I'm plugging the sine function into the cubing function, and when I take sine function, I plug it into x to the third. That would give me sine to the third x. First and foremost, as a reminder, that composition is not a commutative operation, meaning order matters. Well, what we are going to do is we're going to differentiate functions that we can represent. So I'd be given either this function or this function down here, and the idea is we have to recognize it as a composition. And not only that, I have to recognize the order of the composition, meaning let's say I look at the function, I'll call it h of x is equal to e to the tangent of x. Well, what I want to do is I want to represent this function as a composition, f composed with g, and I want to identify what is f and what is g. So not only do I have to recognize that it is a composition, I have to recognize what the functions were that we took the composition of and the order before I can even apply the chain rule, before I haven't even stated it yet, right? Well, if I look over here at these examples, the function that I'm plugging in was the function on the right-hand side, and notice that was the inside of the function. And I'm using this inside informally here. Sine was the outside, x cubed is the inside. What did I plug in? Well, over here I plugged in x cubed, and that was the function on the right. If I look over here at this example, I plugged in tangent, and g is the function that's on the right-hand side. Therefore, this would be tangent. And what did I plug it into? Well, I plugged it into the natural exponential function, meaning f of x would be e to the x. Therefore, when I take the composition f composed with g, I get e to the tangent. Okay, so I recognize what it was composed of. One more example before we get to the statement and applications of the chain rule. Let's say h of x is the square root of x squared plus 3x. Okay. What are the functions I took the composition of to obtain h of x? Again, I want h of x to be written in, so just to establish our notation, it would be f composed with g. Of course, I could do g composed with f. It just means that f would be the function I'm plugging in. But just to be consistent with this previous example, I'm plugging f of x into the function, or I'm plugging g of x into the function f, and let's identify what's what. Well, what did I plug in? Okay. Well, if I look at this expression here, x squared plus 3x was plugged into the square root function, meaning g of x would be x squared plus 3x, and f of x would be the square root of x. That means I took g and I plugged it into f to obtain h. Okay? So this is the first step, is I have to recognize that it is a composition, what functions we composed, and the order that we composed them in. Now we come to the statement of the chain rule. Okay. I'm going to write just the result of the statement. I'm not going to get into the technical requirements that the functions have to be differentiable at certain points or on intervals or anything like that. I'm just going to give you the statement of the chain rule. And that says if I take the derivative of a composition and also I'm going to interchange Leibniz's notation with prime notation. So if I take the derivative of f composed with g, what I do is I take the derivative of what we refer to informally as the outside function, so what I'm plugging into, f prime. I use the same input g of x, and then I chain along the derivative of the inside function, meaning g prime of x. Okay, so I've got two derivatives, product, and a composition. So there's a bunch of different things going on here, and we'll go ahead and we will practice with a bunch of those. All right, let's take a look at the following example. Let's look at the derivative of sine of x to the third. And we're actually going to do this one twice. I'm going to, since this is the first example and I just laid out this formula that's fairly complicated, I'm going to show you all the different bits and pieces here, and then I'm going to show you in practice how we'll actually compute it. As I mentioned before, we have to recognize the function that I'm starting with as a composition. And we can see that I've got x to the third plugged into the sign. That also tells me what f is and what g is. Of course, we've already done this example, so we know what f and g is. But let's pretend this was a new example, right? F of x is what I'm plugging into, and g of x is what I'm plugging in. Now, of course, the functions are arbitrary. We could do g of f, but I'm just going to, for the sake of consistency, I'll just do f of g for all of these. So f is what I'm plugging into, and g is what I'm plugging in. Well, I plugged x cubed into the sine function. Okay. Now, if I look at the result of the chain rule, so this right here is f composed with g. We can see that we need a variety of results up here. What is f prime? Okay, well, f prime of x is the cosine function. I also need g prime. Okay, g prime is 3x squared. Well, then if I look up here, I've got all the different computations. Now we just have to put the pieces together, and we see that there's two factors here, f prime of g and then g prime. The first factor, f prime of g, means I take the function that I the result of differentiating f, which is cosine, and I plug x to the third into that. Okay, so the result of computing the derivative would be cosine of x to the third. That's f prime of g, right? F prime is here, g is here, multiplied by g prime. So multiplied by 3x squared. And usually when we have an expression like this that's multiplied together, there's sort of a standard ordering to things. Multiplication is commutative, so I can write it any order I like. Usually I put constants on the far left, and then I would do, say, powers of x. And then we would do, say, trig functions, or maybe it's logarithms, exponentials, whatever the case may be. But usually we would put it in this sort of an order. Not that this is in any way incorrect, but usually we put it in, by tradition, we put it into this format. Okay, so this right here would be the result of differentiating sine of x to the third. Now, as I mentioned, I was going to do that exact same question a second time, because usually in practice we streamline this a little bit. And so let me redo that example. And we usually phrase it as follows. I'll identify, of course, the composition, which means I have to identify the outside function, which the outside function is this f of x, it's the function on the left, and the inside function, which would be the function on the right. Once again, outside is sine, inside is x cubed. What I do is I differentiate the outside function first. Notice that's what this says here, f prime. Differentiate the outside function, which would be cosine. Now, what do I have on the inside of that, right? F prime of g. Well, notice that this is f of g, so I leave the inside function alone. That just comes along as an input, so that means I would have cosine of x to the third. And then times g prime, that means the derivative of the inside function appears as a factor, so 3x squared. And then again, I can write it in this formatting. So that was less writing for sure. If it's convenient for you, or if it's helpful, certainly feel free to write out all 4 of those pieces and then write out the formula and kind of write out as much as you need. After you practice with it for a while, I think you'll be able to just kind of go right from here to here. And it might take a handful of examples. All right, speaking of which, let's do another example. Let's differentiate. Another example I mentioned in the first part of the video. Let's look at the derivative of e to the tangent. Pretty sure, I'm just kind of making these up as I go. I'm pretty sure that was it. Regardless, that's the one that we'll do. Notice that tangent is plugged into the exponential. That means tangent is the inside, the exponential is the outside. Therefore, if I follow along with this formula, this says differentiate the outside, which is the exponential function, and of course the derivative of the exponential function, specifically the natural exponential function, is e to whatever's inside, right? The derivative of e to the x is e to the x, so this would be e to the x composed with the inside, which was tangent, and then multiplied by the derivative of the inside, which would be secant squared of x. Okay, and typical formatting for this one is I would put the trig function followed by the exponential. Again, it's not incorrect to leave it in this form, but this is more of a traditional way to write it. Okay, let's do a few more examples. All right. Let's look at computing the derivative of the cube root of, let's see, what haven't we used yet? We've done exponentials, we've done some trig functions, here's a radical. Let's do a hyperbolic function. Let's do the cube root of the hyperbolic cosine function. Okay. cube root would be what I'm plugging into, therefore my outside function. The hyperbolic cosine is the inside function because that's what I'm plugging in. And therefore, when I differentiate this, I'm going to differentiate the cube root function first. Now, one thing that I always suggest to my calc students is to rewrite a radical in terms of an exponent. Of course, it's not required because if you just know that it's the 1/3 power, but I think it's usually helpful for them to specifically see that. And then when I differentiate something to the 1/3 power, of course, using the power rule, the exponent comes down, and then the exponent reduces by 1, so that'd be -2/3. The inside function stays the same, right? I'm still composing. Remember, in my chain rule, the first factor had a composition, and the inside of the composition was the same as the original composition. So that means it's just hyperbolic cosine. And then the derivative of the hyperbolic cosine would be the hyperbolic sine. Okay? And then we could certainly clean this up, make this negative exponent positive by flipping that to the denominator. And we could also have this 3, which is in a denominator multiplied through to the cosine. Therefore, we would have the hyperbolic sine divided by 3 times the hyperbolic cosine to the 2/3 power. And that would be the derivative of this original function. Okay? All right. Now, we've done, I don't know, at least 3 or 4 examples so far. I haven't really kept track. What I want to take a look at is, well, what if I have something inside of this x here? So what if not only do I have a composition, let's say like a cube root and hyperbolic cosine, where I have got 2 functions here, what if I have another function inside of that one? In particular, let's just look at this, the function h of x is equal to, let's say, e to the sine of x to the 3rd. Okay? And one reason why I do this specific one is because we already know what the derivative of sine of x to the 3rd is. Okay? Well, I know that this is a composition of the natural exponential function with sine of x to the 3rd. I also know that sine of x to the 3rd is another composition. This is the composition of 3 functions. And here's how the chain rule works in this particular case. All right. Well, let's start by ignoring the fact that we've got 2 compositions, 3 functions. Let's start by just saying, okay, well, it's a composition of e with something else. And the sine of x to the 3rd is just what I'm plugging in. That's sort of like my input to the natural exponential. Take the derivative of the outside function first, which is e to the same input. And then I'm going to take the derivative of the inside. Well, let's ignore the fact that we have to use a chain rule here. We already know what the derivative of sine of x to the 3rd was. Remember, that was cosine of x to the 3rd times 3x squared. Right? This is from a previous example. Well, what this shows me is that when I've got 2 compositions, I'm going to use the chain rule twice. Okay? We use the chain rule for this first composition, which is e to whatever's inside. That's a composition. And then when I bring out the derivative of the inside function, my quote-unquote g of x, this was also a composition, so that required a second use of the chain rule. Let's do one more example with multiple functions. Let's do the derivative of the following. Tangent of sine of e to the square root of x. All right. Well, first of all, let's recognize that this has compositions. I've got tangent as my outside function. I've got something plugged into that. Plugged into is just another way to say it's a composition. So inside of the tangent, I've got a sine. Inside of sine, I've got the natural exponential. Inside of the natural exponential, I've got the square root function. Well, how many compositions is that? All right, well, let's see. Root x is plugged into the natural exponential. There's one composition. That is then plugged into the sine function. There's two compositions. That is plugged into the tangent function. That's three compositions. All right, well, previous example had two. This one had three. So therefore, this is going to require three applications of the chain rule. Let's go ahead and compute that. We follow along just the same way that we did in the previous one. I just do it an additional time. I start with the outermost function, the tangent. Its derivative is secant squared. And then everything that was inside of the tangent is still inside of this function, meaning sine of e to the root x. Okay, now multiply. Now what I look at is the inside of the secant squared, so the inside here. And I look at the outermost function, which is the sine function. Take its derivative, which would be cosine. Everything that was inside the sine function is also going to be inside the cosine function, giving me e to the root x. Now another application of the chain rule. I go to inside of this function, which is e to the root x. The outside function here would be the natural exponential function, whose derivative would be the natural exponential function. The inside, the inputs are the same. That would give me root x. And then finally, take the derivative of what was inside that, which comes out as a factor, 1 over 2 root x. Okay. Now, when I do this in the classroom, usually my very last example, I'm limited here in space, and also I don't want to make this super long, is I'll have one where there's like maybe 6 compositions, and it just looks like this horrific function. And you're like, how in the world am I supposed to differentiate that? And you just do one step at a time, and it's really not a big deal. So chain rule multiple times is really not that much more difficult than just doing the chain rule once, okay? Unlike the product rule or the quotient rule. But at any rate, thank you for watching, and please consider subscribing.